I was that kid who never outgrew the why phase, but it wasn't until I found science that I found my answers and more questions. Science is an infinite process, and that's why I love it so much. When I came to Duke, I chose to come to a place that would further foster my curiosity. I first got interested in computer science specifically when I was in the 7th grade. I took this elective course on futuristic thinking, and I was enthralled by artificial intelligence. I mean, these programs transcend human knowledge. I went home, I bought a textbook, and I started teaching myself to code. When I was in 10th grade, I found yet another source of inspiration. My cousin was diagnosed with breast cancer, and I saw firsthand how much this disease impacts a woman and her family. I knew that I wanted to get involved and use my passion for computer science to improve the breast cancer diagnostic process. 1 in 8 women will be diagnosed with breast cancer in their lifetime, and these statistics are just startling, and unfortunately, they're on the rise. Early detection is instrumental for treatment success. I was particularly interested in answering one question: is a breast mass malignant or benign? I wanted to answer this question by creating a tool that works with fine needle aspirates. Fine needle aspirates are the quickest, the cheapest, and least invasive biopsy a woman can have. However, they're wildly inconclusive, so a lot of doctors refuse to use them. There are a lot of subtle patterns that go into reading a fine needle aspirate, and artificial neural networks have the capacity to really detect patterns that are far too complicated for a human to recognize. That's how I decided to apply this sort of algorithm to the fine needle aspirate problem. Once I had created Cloud for Cancer, I wanted to deploy it to the cloud because the cloud is just this incredible elastic entity that can be used to support any hospital in the world at the same time logging on to use the tool. The other thing that's really great about the cloud is it's really flexible. So currently, Cloud for Cancer exists as an online browser app. But in order for a tool to be viable, it has to be easy to access. So if doctors are using existing mobile apps or old medical systems, I can easily build a piece of front-end code and put my program into that system. So how exactly does Cloud for Cancer work? It feeds in a series of logical inputs that are based on how the cells look. Are the cells mono or multi-layered? Because monolayered cells are usually an indicator that a mass is benign, whereas you see a lot of multi-layered areas in cancerous masses. Other inputs might include marginal adhesion, how much the cells are sticking together, or the chromatin texture, fine versus coarse. To give you an idea of what fine needle aspirates look like, this particular mass is benign. And as you can see, the cells are about the same size and about the same shape. That would be an indicator that the mass isn't cancerous, which it's not. But the nucleoli, which are those dark dots, are very prominent, and there are multiple ones per cell. You usually only see that sort of characteristic in a cancerous mass. For contrast, this is a cancerous mass, and I think that the really cancerous attribute here is that the reproduction is going wild. It's not very regular at all. However, the really light cells are devoid of their cytoplasm, and that's usually an indicator that a mass would be benign. So again, you have this really complicated pattern where cells are exhibiting both types of characteristics. With that knowledge, what do you think this mass would be? It looks different than both, but it's actually benign. And the benign characteristic it has that's pretty prominent is the marginal adhesion. All the cells are close together. But the multi-layered areas are usually only found in malignant masses. I show you this to show you why Cloud for Cancer is needed. These masses can be hard to detect. The way it works is it feeds in a series of 9 inputs based on how the cells look. And in the artificial input layer and the hidden layer, all of these connections are actually math. And the neural network is able to learn based on its experiences and mistakes what the optimal algorithm and what the optimal weightings are so that it can reach a diagnosis that's accurate. In its current iteration, Cloud for Cancer is almost 5% more successful than any commercial products. I've also run a series of 7.6 million trials, proving that as I get more data, these statistics will go up. I'm partnered with 2 different partners who are giving me additional data, and at current, it's over 99% successful at diagnosing cancer patients. Since coming to Duke, I've really had the opportunity to make Cloud for Cancer grow. I was already really passionate about science, but I hadn't thought a lot about the bioethics component. And since coming to Duke, I've realized that Cloud for Cancer makes the most sense to exist as a nonprofit, and I have started a nonprofit around this work. In the third world countries, the only means for diagnosing breast cancer that they have in a lot of instances are fine needle aspirates. So it's really imperative and pivotal to make sure that it's accessible to those doctors. Additionally, I've extended Cloud for Cancer to work with diagnosing other diseases. Leukemia, particularly mixed lineage leukemia, is very aggressive, and there are no specific targeted treatments for it. I use genetic expression profiles, which means that there are over 200 inputs to the neural network. And with some tweaking, I was able to get really high diagnostic success. It's a small data set, mind you, but it diagnoses 100% of the masses correctly. And it was able to identify 4 proteins that may be candidates for drug targeting. So I'm really excited about where the potential for Cloud for Cancer as a research and biomarker discovery tool might stand. However, for me, science is this iterative process, and that's why coming to Duke, I knew that I was going to do both Cloud for Cancer and other sorts of discovery. I've been working in the Center for Applied Genomics and Precision Medicine for the past 2 years under the mentorship of 2 incredible researchers, Dr. Jeff Ginsberg and Dr. Ashley Valente. And what's really neat is even though they're some of the leading researchers in the field of precision medicine, they're really passionate about pulling undergraduates in and making sure that I have a piece of our project that I can really take ownership over and express my curiosity and creativity with. We're really interested in looking at immune response and different mechanisms. My piece of that puzzle is differential exon usage. So there are these messenger RNA strands, and if they're tweaked a little bit, they might confer different immunities. Basically, what we're looking at is how the body responds to exposure to certain pathogens, including influenza and bacterial pneumonia, both of which can be deadly and are both really interesting to study in tandem because one's a viral pathogen and one's a bacterial pathogen. Although we don't have our pneumonia data back yet, we've identified 63 biomarkers for differential exon usage in influenza patients. I'm headed back to Duke in 2 days where we'll actually be using these biomarkers to build classifiers, and our overarching goal is to try to predict whether somebody will get sick with influenza before they even recognize that they're sick. So you could treat somebody without them having to undergo any of the symptoms, negative ramifications, etc. As a Duke student, I have absolutely thrived in lab, and I know that I leave a more curious person. But I've also enjoyed participating in a wide variety of activities that have really helped me grow as a person. I'm in a selective living group, which has become my family away from home. I actually tented for the Duke-UNC game this year, like any good Duke student does. And I've been able to be involved in a lot of volunteering initiatives to get other women interested in code, one of which led me to the White House with Tom Hanks having middle school girls code the pattern of the Christmas tree lighting. It's incredible the sorts of opportunities that Duke students have. For me, I know that I leave Duke really passionate about genomics, something I think I developed through our Focus program. And I love the idea of solving big data problems to really find cures to some of the country's and world's most pressing disorders. My goal is ultimately to be a pediatric oncologist who is on the frontier using big data to really find novel treatments. I'm so excited that I was able to share with you guys today, and thank you so much for supporting Duke.